Earlier, we discussed how to compute the electric field in the case where the source of the field was a single point charge. In this lecture, we're going to learn how to calculate the electric field in situations where the field arises from more than one point charge. To do this, we will use the concept of superposition, which not only will show up repeatedly in this course, but also arises frequently in other contexts in science and engineering. First, as a warm-up, let's try to answer the following question. Imagine that an electron is placed at location A and experiences an electric force in the direction shown by the arrow. Choose the number next to the arrow on the rosette that best represents the direction of the electric field at location A. The answer is arrow number 4. Let's go through the reasoning for this. Recall in an earlier lecture where we introduced the idea of the electric field, we mentioned that the electric field itself is not enough to describe the electric force. There are two things that we need to describe the electric force on a charge. One, the sign and magnitude of the charge itself, which we will represent as a non-zero scalar Q that could be positive or negative, and two, the electric field at the location of the charge, which we will represent here as vector E. Mathematically, the electric force on the charge is equal to the product of the charge Q and the electric field E. This vector expression tells us that if the charge Q is positive, then the electric force and the electric field must point in the same direction. However, if the charge is negative, then the electric force points in the direction opposite to that of the electric field. Since in this example, the charged object is an electron, which has a negative charge, and since we see the electric force points in the direction of arrow number 8, then we know that the electric field must point in the opposite direction. That is, the electric field must point in the direction of arrow number 4. Now notice in this question, we didn't say anything about the source of the electric field. We do know that the electron itself cannot be the source because, as we said earlier, a charge can exert a force on itself. If the source was some other point charge, then we could describe that field using the expression for the field of a single point charge that we discussed earlier. But what if there is more than one point charge that contributes to the electric field at a given location in space? How would we describe that? Here's how. The key idea is that when the total electric field at a given location in space arises from multiple point charge sources, then the total electric field, or net electric field, total and net mean the same thing here, is just the vector sum of the electric fields of each point charge source acting at that same location. To say it another way, the electric field due to a given source point charge at a given location is unaffected by the presence of other source point charges. We can calculate the electric field of each source point charge just as if the other source point charges didn't exist. Then, to get the total electric field, we simply superpose the fields of each charge. That is, we just add up the fields vectorially. This concept of superposition, the total effect is just the sum of the effects of each part treated independently, often fails to describe properly many physical phenomena. However, here, for us, it works beautifully for electric fields and, as we will soon see, for magnetic fields too. Let's do an example where we calculate the net electric field at a specific location, marked by an X, due to 3 point charge sources, Q1, Q2, and Q3. Let's write down the charges in terms of a common charge magnitude Q greater than 0, with Q1 equal Q, Q2 equal to 2 times Q, and Q3 equal minus 4 times Q. Let's also write down the distances using a common length d greater than 0, where Q1 is at a distance d from location x, Q2 is at a distance 2d from x, and Q3 is a distance 4d from x. We will first calculate the electric field at x due to each source charge, one at a time, ignoring the other source charges. For this, we will use our expression for the electric field due to a point charge. We will start with Q1 and represent E1, the corresponding vector electric field at point x due to source charge Q1, using an arrow. The length of the arrow represents the magnitude of E1 at point x due to source charge Q1. We can also write down the magnitude of E1 symbolically as shown. The direction of E1 is represented by the direction of this arrow, which points away from Q1, as it should since Q1 is positive, along the line joining point x with the location of Q1. Now we can repeat this whole process, focusing only on Q2 with a corresponding electric field E2. Here too we can write down the magnitude of E2 symbolically. We notice that the magnitude of E2 is 1/2 the magnitude of E1. So we will represent the vector E2 with an arrow whose length is 1/2 of the length of the arrow we use to represent the vector E1. The direction of E2 is represented by the direction of this shorter arrow, which points away from Q2, as it should since Q2 is positive, along the line joining observation point x with the location of source charge Q2. Let's repeat this process one final time with Q3 and with a corresponding vector E3 at observation location x. Once again, we can represent the magnitude of E3 symbolically. And we see that the vector E3
has 1/2 the magnitude of
the vector E2. So we will represent the vector E3 with an arrow
that has 1/2 the length of
the arrow we use to represent the vector E2. The direction of E3 is represented by the direction of this arrow, which points toward Q3, as it should since Q3 is negative, along the line joining the observation point x with the location of Q3. Now we simply superpose these three electric fields to obtain the net electric field. That means we simply add the fields, in this case by graphical vector addition, by adding the arrows representing the vectors in the typical head-to-tail fashion. The vector sum is the total electric field, the net electric field that we wanted to find. Let's make a couple of comments here. First, notice that with the net electric field in hand, we can now calculate the electric force on any charge that is placed at location x. So, for example, if a charge Q5 is placed at that location, the electric force on Q5, the vector F5, is found by simply taking the product of Q5 with E net. If, however, a different charge, say Q6, was located at x, then we could easily find F6, the vector electric force, on Q6 by taking the product of Q6 with the same net electric field. Bottom line here, if we can assume the source charges don't change, then we only need to calculate the net electric field once for a given location. After that, we can just use the same electric field to calculate the electric force on any charge that happens to be at that location. That's one of the advantages of calculating electric fields. Second, you might be concerned that interactions between the source charges themselves may mess up these calculations. As one example, we know there is an electric field at the location of charge Q2 due to Q1, and therefore an electric force on Q2 due to Q1. The same holds true for an electric force on Q1 due to Q2, an electric force on Q3 due to Q1, and so forth. Won't all these electric forces cause the source charges to move around? For our purposes, we're going to take the answer to that question to be no, and we'll justify this by making the reasonable assumption that each source charge is nailed down and doesn't move. To say this in a little more sophisticated way, we'll assume that the net force on each source charge, which is the sum of the electric forces and possibly some other unknown forces, is always zero. Thus, if the source charges start at rest, they remain at rest, and so our calculation of the net electric field doesn't change in time. It would be good to do an example of the vector addition of electric fields from multiple point sources where the charges and locations are specified using numerical values. We'll save that example for another lecture.